HPC workshop. Welcome back from your break. I hope it was a little bit relaxing. So we'll go into the next session very shortly. Our online participants, I believe you're back as well. Okay. So in this next session, Engineer Bola Akanle. Okay. Engineer Bola Akanle will be taking us in this next session, and at this point we'll be taking, a deep dive into the core HPC from this point onwards, and I believe it will be very impactful and interesting. You're welcome back. Thank you. Let's put our hands together for ourselves. Can we welcome Engineer Bola?
Yeah, thank you very much, Dr. Hoshi. Once again, I want to welcome us back from our lunch. And like I had the other time, I hope we all had a wonderful lunch. We'll be going into the next section. If we look at our timetable. Sorry. So we call it a refresher on intermediate HPC. So what we want to be discussing this session between 2 to 4 is to just have a kind of overview in another format of what we had for in the last workshop. 2 weeks we discussed about building high performance computing. So it's more or less like a refresher of what are the components of high performance computing, what we use them for, the definition, and then what it takes to build high performance computing, so that by the time we start using it and mentioning some terms, we are all familiar with it. That is what this session is all about. It's not a practical session, but it's just like an information session. Are we all on the same page? Yeah, so that's the essence of this. Please, can I see my slide? Yeah. So, because in the last workshop, it was all about building high performance computing. That is what we centered on, and we discussed quite a number of things around this area. So that's why I just titled it Building a High Performance Computing Infrastructure. Like we all know, we've given the definition of high performance computing, but let me just reiterate it again. We said high performance computing most generally refer to the practice of aggregating computing power in a way that delivers much higher performance. The other time, one of us was asking what's the difference between high performance computing, a data center, and cloud computing. I believe we all have a full understanding of the difference between the three. Do we all have, this is an interactive session and an information session, so that by the time we are diving in, we have a good understanding of our terms and terminology, and we are not mixing things together. So you can also take this class as an information session, so that we are all familiar, because we have some of you that you are not familiar with some of this terminology. So like I said, high performance computing is generally referred to as the practice of aggregating computing power in a way that delivers much higher performance. So high performance computing, most time we look at it like a cluster of computers using each resources in each of these computers, most especially the computing resources. You might have more than one server in a data center. So data center is more or less like a house that houses those servers. That is what a data center is all about. A data center is a location where you have all your computing devices that houses all both your switches, your servers, what have you, your routers. That is what a data center is all about. Do you get that? Then you, in a data center, you can have your high performance computing infrastructure inside a data center. Am I communicating? You can have all your high performance computing infrastructure inside a data center. So don't mix the two together. So now when we now talk about high performance computing, you are aggregating all the computing device, computing resources in each of those servers, because you can have more than one server in a particular data center. So aggregating those resources together for you to carry out your computation, that is what we refer as high performance computing, because you are now going to be able to use it to perform tasks that ordinary computer wouldn't have, or ordinary server wouldn't have been able to achieve. Then you're able to gain time in your processing. So do we all understand what high performance computing is now? Do we all have an understanding? Like, for example, I have this machine here. This is a laptop. This is another laptop. This is another laptop. So aggregating this laptop together so that I can use the processor here, the RAM here, the RAM there, as if it's still one device that I'm using. So aggregating the resources together to carry out a task. Do you understand? So then you now be able to have what we call high performance computing. Am I okay? I'll be talking as if we don't have any, so that we can all, those people that have lower understanding, as in they can also understand what we are doing. So do we understand what HPC is all about now? Because that's the fundamental. We call it high performance computing workshop. So it will be nice that you don't even know what that high performance computing is all about. So that's why I'm taking my time to let you know what high performance computing is all about. And when we talk about this high performance computing, okay, let me first mention some of the resources in high performance computing. We talk about the processor. You know, your computer device, you have, in your servers, you have computers, you have RAM, you have other resources that you have in a single server. Hard drive, you have quite a number of resources, exactly. So, the slide. So in a requirement for setting up an high performance computing cluster now, if you want to have high performance computing, there are some certain things that will come together to form your high performance computing. So we have your compute node, you have your storage, you have your network infrastructure, you have your job queuing system, and then you have some other software. These are major components in high performance computing. We know we use high performance computing for processing, for simulation. Do you understand? So in this case now you have your compute node. What we call compute node are more or less like those things that will be doing the computation, the machine that will be doing the computation. Some of you talk about data analytics. So that means it's the compute node now that will be doing all the data analytics that you are talking about. Do you get it? That's the work of the compute node. And it always comes with high processing capability with GPUs. Do we know what GPU are? Do you know what GPU, who can give us, like anytime I'm talking like this, I always like to make it interactive. GPUs, have you heard of GPU before? If you have not heard of GPU before, let me see your hand up. Please don't be ashamed. We're all here. I can learn from you, you can learn from me. Let's take it that we never be ashamed or just be open up so that we can, at least to your own level, we can come down there, and at the end of the day, you get something to understand. If you have not heard of GPU before, let me see your hands up. Okay? So who can tell me what a GPU is? Okay.
Should I start? Okay. GPU stands for graphic
processing unit. It's a specialized processor in computers that processes images, but then it does so in parallel computing. So it's mostly favorable in HPC where we need to run some analysis in parallel way.
Thank you very much. So let me hear from you. But you've heard of CPU too. Okay. So someone will tell me the difference between the
I would say just like the CPU, GPU also works in the same way, but it does its processing in parallel. So it does basically they use it for processing calculations in numbers. So instead of being it mobile, probably you have multiplication tables now. 2 times 1 is equal to 2, 2 times 2 is 4. So instead of being for a CPU will take 2 times 1 first, 2 times 2 first, second like that. So it take you one at a time. But for GPU, it takes all those 2 times 1, 2 times 2, everything, take it together, then you do everything together in parallel.
Thank you very much for those contribution. Yes. Any other contribution? Central processing unit and graphical processing unit. So yeah, that's the basic. Let's take it that way. That's just the basic. The GPU will do your work faster than what your CPU will do. But there are times that the kind of processing you want to do, GPU will not do it for you. Despite the fact that you want something to do your processing for you faster. There are some processes that still prefer to use just ordinary CPU. That's why in some server you hear about 14 core, 15 core, 16 core, 48 core, 64 core. So that will determine, we are going to do that in this class when we start parallel programming. You will see how to aggregate processing power together to carry out your analytics. So that is that about compute node. Then we now have our storage. Before you can do anything, even on your computing devices, I mean your compute node, you need to have what we call a storage because you want to process some data. That means those data must reside in a particular place. Let's talk about people that do genomics because they have heavy data. So what do? You have your data stored somewhere before you can pick them up for your processing. So that's the work of storage. The storage keeps all your data that you manipulate. Do you get it? That is what the storage node is all about. Then you now have your network infrastructure. We talk about that the compute node is meant to do what? High performance computing is the aggregation of computing resources. So to bring about, to make all these devices communicate together, like I was giving an instance before, you have these 3 computer sets here. You need to interconnect them together. So that is where the network infrastructure comes to place. Am I communicating? So that's what the network infrastructure does. Then you now have job queuing system. There's what we call scheduler. There are times that your the processing capability of your infrastructure or your high performance computing might not meet the demand or all the demand that is needed to do at a particular point. So you need what we call a scheduler, so that at every point in time, you have a queue of different jobs to be done. So you can say, okay, let's assume this man has, my brother here has something he wants to process. He also has something to do. But you realize that this compute node, your high performance computing cannot do everything at the same time. What the scheduler does for you is to just keep those jobs in queue or give priority to those things you want to do. So any high performance computing infrastructure you have, you need to have something that does the scheduling for you so that it can help you. It's more or less like a traffic controller. What do you call it? Traffic. The traffic warden, exactly. It's your turn, go. No, you wait. Come first. Oh, this is the priority. The president is coming. Stay. Go. This one is of high priority. That's what the scheduler does. Do you get it? Then you now have the software. So the software, now you have different software that you will use for your processing. You can, depending on your area of specialization. Geophysics has their own. An ICT person, you have machine learning, different kind of machine learning application. a physicist too has his own, a petroleum engineer too has his own. So we have different kind of application that can be installed on our server to do all this processing for us. So do we get that? So any question before I go forward? I don't want to be going. Question? Okay. Make comment, exactly.
You mentioned CPU and GPU for compute. And can you also elaborate on the place of TPU, Tensor Processing Unit, which is also very core to high-performance computing now? And you know there are accelerators. So maybe you can just elaborate on that so that persons who have a broader idea of what the compute can also comprise of. Okay, so like the TPU is Tensor Processing Unit. It was actually an initiative by Google, okay, and is to carry out computations in Tensor. Everybody here knows what a scalar is, know what a scalar data is. Like if I say 1, 2, 3, 4, those are scalar data. Then from scalar you can have vectors. So if you want to capture vectors, you capture it as an array. And of course, you use like matrix multiplication now, is done with vector. Okay, and it helps you to capture chunks of data, massive chunks of data at the same time. But beyond just the vector, you can go into tensor. That's 3-dimensional. So they built those TPUs so that you are able to process like 3-dimensional data at the same time, rather than just processing 2D data. And that makes processing to be very fast. In fact, the data center that Google is building currently, they are leveraging largely on TPUs. Is that okay? So that's just to add that.
Thank you very much, Professor Adetiba. You will talk better as a researcher. He's also a system administrator, so it's all encompassing. But me, I'm not as the research he does. Me, I'm just a practitioner. I do system, all those. So that's why I push it back to him. Okay. He's also a prof, a researcher, all in one. And a person. Okay, thank you very much for the. Then you also talk about the accelerator. For me, the way I also see accelerator, you will also add to it. I also view them as GPUs too. That's the way I always look at. Anytime I see accelerator, sometimes I look at it as if it's more or less referring to as GPU. I don't know your view about that.
GPUs actually does acceleration, but there are also DSPs, that digital signal processors, that complement computation that are done by your CPUs. There are some computation that are better done with DSPs. So DSPs are added to augment the capability of CPUs. Okay, just to add that too.
Thank you very much. Okay. Please, I need us. We have more than one mic, so please let me give it to him.
Yeah, so you said some computations are better done on CPUs and some on the ESP you mentioned. Can you elaborate on it? What operation, like, can you give examples? Okay. Yeah, I think I was talking about if you are familiar with machine learning, for instance, when you are doing your input data will be captured as matrix, and the computation within the neurons now. You are carrying out matrix operations majorly, summation of the different inputs that are coming to the neurons. So instead of treating each data as a single data, so you can have a vector of data so that you have several data you are processing at the same time. Then beyond just a vector, you can handle an entire matrix at the same time. So CPU can handle that. But TPU also takes you beyond just the 2-dimensional data. There are some data that, like if you want to process image normally if you have RGB, that's a 3-dimensional image. The R is a channel that will range from maybe 0 to 255. The G is also a channel that ranges from 0 to 255. And the B is also a channel that ranges from. So instead of
processing channel by channel. In terms of processing, you can process the whole data at the same time. And TPU is designed almost for that. So if you are able to do that like at the time, you understand, you have a variable that you can instantiate as a 3D variable. And you are able to process everything at the same time, compared to when you are processing just a one-dimensional vector. Which one will be faster? The 3D. So that's exactly what CPU does. The accelerator, yeah, there are some signal processing, maybe floating point. You were talking about flops the other time. There are some use cases, some works you are trying to do that will require high level of precision. That means that instead of doing like 8 bits, you may want to go 64 bits. You understand? So, and you may need accelerators to be able to process to that level of precision. Is that okay? I hope I'm not going to. Okay.
I just want to talk about the TPU. You know that when we are talking about the CPU, the performance of the CPU is directly proportional to the power consumption. So GPU perform faster and more efficient than the CPU and have higher power consumption. But TPU perform higher performance and calculation, but it consumes low power. That's the basic advantage of TPU.
Okay. Can we get that very well? Do we understand what you just said? So please add it to your knowledge. Thank you very much. So are we all on the same page now? Please get it very well. No, it has higher power consumption than the CPU when it's doing its processing. But for the tensor, it consumes lower power compared to the GPU. CPU, yeah. Tensor power. The computation. You have something to say? Go ahead.
Okay, my question goes like this. You said Tensor was developed by Google for tensors. I think that's the data structure they use to store their own vector. So let's say I'm coming in from probably Facebook Touch background now, Touch for deep learning. Can I use this same TPU on Facebook Touch?
Okay. Your HPC would have the compute resources that are available there. So it's not all HPCs that have the compute that has TPU. Is that okay? Like the HPC we'll be using for the practical now, we have multi-core processors there. So that means there's no TPU on it. So anything you want to do that requires TPU, you can't use such HPC. But there are some, like if you have Google Colab has provision for TPUs, for GPUs, for CPUs. So, but for basic users, they won't give you access to TPU, except to now subscribe. Exactly. So that's just it. Okay. Oh, exactly. You can. Yeah, you can. You can. Okay. I think that's
Thank
noted.
you very much for all the contribution. Yeah. So next, the slide, please. So we're talking about high performance computing. So there's what we call HPC clustering of HPC. Do we get it now? So you know what clusters mean, bringing things together. Do you get it? So anytime you are talking about high performance computing, it has to do with clustering of servers with high processing capability to work together. So like I was describing the other time, bringing these computational resources together is what we call clustering. Anytime you hear this word, you have an understanding of what they are talking about. Clusters of HPC. Do you get it? Now, this is, for example, this just how HPC work. I want us to look at this very, very well. I've told us what made up of high performance computing. So just look at this very well now. you have your servers. That's what we call your compute node. And then in this compute node, you can see you have various, you even have some might just be with GPU. You have some with CPUs. That is your compute node. And at the end of the day, you find all of them connecting together to give you what you want. You also have your storage here. This is your storage. Then you have, okay, you see I have compute node now. These are specialized compute node. Okay, we call this specialized because probably they come with GPU and probably the TPU also. So you have some specialized device. Then you have the ordinary server that just come with cores of compute resources. So you can just refer them as normal servers, but have high computational resources. Then this one will come with GPU, TPU, and some other specialized kind of resources. Then you now have what we call, okay, if you can remember in our last HPC workshop, we talk about logging. When we're talking about LDAP, if you can remember, we talk about LDAP, having single sign-on. You can implement all that in a standard high-performance computing infrastructure. Then you have the different user connecting to these resources to use. Then you have your data transfer node. So if you want to do your data transfer, there's what we call Globus. How many of you have heard of Globus before? Globus. Okay, when it comes to, let's assume that, just like I said, just get this time because we are talking about high performance computing. So there are some terms I will be mentioning as I remember them or as they come to my mind, so that you also add it to your dictionary. Globus is an infrastructure or is a network, GLOBUS. Is actually used for data transfer and is available, is more or less like a very big network. You install a Globus in your own environment. So if you want to do a data transfer, large data transfer, probably between US and maybe a researcher in the US and you are in Nigeria here, and you want to receive large volume of data, you know, you can't just send it via your email. You understand what I'm trying to say? Maybe you can be talking about like 500 gig of data, 1 terabyte of data. So you actually use this kind of node to transfer data between those two researchers. You are in Nigeria here, you need a data from US researcher. So you use your Globus to do a data transfer. There are other ways, but Globus is one of the most accepted ways of doing large data transfer between researchers. So what you do is that you install Globus in your own infrastructure, in your own data center, and then you use that between the two of you to transfer data. You can read more about Globus after the class. Like I said, we are just mentioning these things so that it's an information session. Then you can also use file transfer. There are different types of file transfer protocol that you can use, but Globus is one of the best that you can use to achieve this goal. So now we have talked about high performance computing. So we have different types of high performance computing. So we have the dedicated supercomputer. We have the commodity HPC cluster, like the one we talk about. You have HPC in the cloud, like Prof was saying, Colab. You can actually access these resources in the cloud. Now we're saying the other time, we mentioned data center. You know, someone asked the question, and I want to always refer to it. I asked the difference between high performance computing, data center. Now I'm not talking about HPC in cloud. So who can tell me, you've been hearing the word cloud, 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 cloud. So what is a cloud? With relative to what we are discussing here. Cloud. Please, can you give him mic? Please, it's an interact, because when we discuss this thing, you get to understand it very well.
Do I need to stand up? No. Actually, cloud, when we talk about cloud in IT, we are not talking about the cloud we all know about. So I can say cloud is just someone else's hard drive. Accessing someone else's hard drive using a third-party software. That's just cloud. I said accessing someone else's hard drive using a third-party software. That's a third-party software. That's the
another person, he mentioned hard drive. That is just an example. Accessing someone computing resources from your own using any kind of application. Like if you want to access, it's just as if you are accessing someone computing resources. That's what it's all about. Like you are accessing another data center elsewhere. You can always say that I'm getting connected to a cloud to do my work, or it's hosting it for me. Do we get it? Any other contribution? Okay, so okay, Daniela. Okay. In federated class, so she should be, and you are here, you don't want to talk. Prof, thank you very much.
Okay. Cloud computing is a kind of delivery of computing services over the internet and can be paid per use. So you have a kind of infrastructures that are already made available for users, and they can be delivered from in two ways. Have infrastructure, can have infrastructure as a service, platform as a service, and software as a service. And users can be accessing all those services by paying for those services that we call now pay per use or pay as you go, and access it over the internet wherever they are at every time, anytime.
Thank you very much. She mentioned some key points. You know, when we talk about cloud, there are some key things you should watch out when you mention cloud. She talk about pay as you go. You access it over the network. What again? From every, it's available as a service and things like that. So you note that means when you talk about cloud, they have some certain characteristics. Do you get it? Thank you. So now we are talking about HPC. The slide, please. This slide. So we are talking about HPC in the cloud. So you can also have HPC in the cloud. You can have it on-premise. Do you get it? So, and what are the major cloud providers that we have? We have AWS, we have Azure, and then we have Google Cloud also. Then we have, you can also have your own private cloud. You can build your own private cloud. Like in Covenant University now, in CApIC-ACE, we are actually building our own private cloud. And even quite a number of our students have done some research around the private cloud. But we are using an open source software to do that. That's using OpenStack, because it's more or less like an OS that can help you to build your own private cloud. So that's part of what we are currently doing in CApIC-ACE as we speak. So that's a private cloud. And you can also have what we call an hybrid cloud. So the private cloud we have in Covenant, we can decide and say that, okay, we want to connect our own private cloud with Google. Maybe we want to share some of our resources. Okay, we have a resource now, but there are other things. Maybe we are running an application. Then there's an application that resides on Google Cloud, and then there's another one that resides here. We can bring those resources together. That's what we call hybrid, interconnecting two different cloud providers. Then you call that an hybrid cloud. Do you understand? Hello? Am I communicating? So do you understand the word hybrid? Bringing two things together from different sources. So that's what we call an hybrid cloud. Interconnecting my own cloud. Probably I'm using Azure. I just decided, no, I want to use Google too. I bring the two together to communicate with each other. So I won't say I'm using only Azure. I will now say I'm using Azure and Google. Not separately now, but I've brought those resources together. Because there is a place you can be using Azure separately. You can be using Google separately. That's not what we call hybrid. But you are bringing the two compute resources together to communicate with each other. You can't say that you are running those applications separately. But when you are sharing those resources together with each other, then you say, I'm using an hybrid cloud. Do you understand? Please ask question. Okay.
There was a comment from, I've forgotten his name the other time, Mr. Olatunji, that maybe he's even using cloud. And he doesn't look like he's using cloud. I remember that comment. And I just want us to take on this cloud computing concept a bit. She mentioned the different service models in cloud. We have platform as a service, we have infrastructure as a service, and you have software as a service. So how many of us have used Google Doc before? Google Doc. Okay. So you are using cloud. That is software as a service. Google Doc, Google Drive. I know almost everybody uses Google Drive. So you are already using cloud. Because those services are available on the cloud platform as software as a service. So I don't think we should bring it home so that it doesn't look like one abstract concept. Yeah, it's provided as it's a mailing cloud platform. Yeah, Google Mail is a cloud service. So just to let us know that we have been using some of us are using cloud on our way.
When you want to register some, maybe on a platform and it asks you that you should register through your Google, what's it called? Google account. You just log in through your Google account and it picks everything from your Google account. Can you call it an IP system?
It's more like a single sign-on. Single sign-on, exactly.
Single sign-on.
Yeah, so that you use it to sign in instead of you creating another account. With that account, you can use it to log in into their own application. So you will discover when you do that, you don't need to type the password again. It takes your existing password. So you are using that same email password to log in into some other application. So that means you have a single sign-on on some application, not anyone that made the application available for you to use such a service. So you call it single sign. That's what we call SSO. Okay. Please take note of all these things. They are very, very important. We are here today. Those knowledge are not wasted. Yes. Just take. How many of you have heard of single sign-on before? Or what single sign-on does? But you know what single sign-on does now.
Okay, this single sign-on, open authentication, I believe. Open authentication, also called open authentication. So when we're talking about security-wise, do you think it has any implication? Yeah, what you just said, open authentication, I'm asking if it has any security implications, because you're using one information for your
Yes, it has security implication. Why I say that, there is something that happened just this last week that somebody called my attention to it. You know, there are some applications you access on the network or maybe in the cloud that actually still asks for your single sign-on, that you can use your single sign-on. Sorry, you can use your email to log into those applications. So of recent, it was discovered that some of those applications were hacked. And that means your username and your email and your password was exposed and it was made available to the public. So imagine those places, somebody can just do a guess and begin to log in. You might not know those applications that you have, but you might just do a guess and begin to use your email to log in into several applications. Luckily, you might just get into one that it will just get all your resources or damage quite a number of things, reconfigure some things for you. So yes, it has a security implication. It has its own advantage and its own disadvantage. But there's quite a number of security lapses to that. So, yeah. Okay.
So if, say, we use the open authentication, like one for all of our accounts, how could us like prevent that attack from happening?
I think for me, for security, you can't. We talk about security as the state of yet undetected vulnerability, right? That means you are as much as secure if you do not know your back door is open. You feel secure. So there is no exact holistic approach in terms of security. I'm talking about maybe single sign-on and all of this. It is an event to make things easier, right? you are not even also expected to just have maybe one password and all of this. But how you can go about that, right? Some sort of other protection. You know there are security layers that you can apply to see that you are fairly secure, right? And some of those could be things like two-factor authenticators. You can use another platform to support. It could even be your device. You send an email to yourself to know that, okay, you are logging into something else using your SSO, and you are fairly protected at that point. So there are various layers you must apply to stiffen the core of your vulnerability, that are more like your attack surface. You reduce your attack surface and without human action.
Yeah, I do understand what you said, but you know, we at one point or another, we all use this open authentication thing. And you know, once you accept to use that open authentication, you just go through your Google account, copy whatever information is there, and paste it in the new account that you want to use. So that being said, you are already vulnerable. Because everything you have, whatever information you have here has been copied to the other end of the application you are trying to log in. So if one person have information to that particular information, so that means all of your accounts that you use that information to access are vulnerable. So how do we prevent that from happening? Can we say that using this one single sign is easier actually, but can we say it's not advisable, something like that? Because it's easier to use that open authentication, but it also has its own risk. Yeah, so how can we prevent that?
Hi everyone. Let me respond to that. Given the fact that it's something that, given the privilege I've deployed that before, so I believe I have right answer for you. The thing is that the system is getting smarter day by day. Not enough, although the essence of the single sign-on is just for you to be able to log in using the same login credentials everywhere you log in. But the thing that you also notice that if somebody by mistake get access to your login credentials, different from the same laptop, it will request to do something, just like he mentioned to you, maybe, okay, look, there's something wrong with maybe something wrong with the signature. What is it? Okay, it may ask you for maybe two-factor authentication. So it's not just about you being careless. Your system also knows, I always get these login credentials from this laptop. But the moment it changes, it begins to suspect. They keep ask several questions then. And the other thing that can be done, and everything depends on the administrator, there are several policies behind which you don't know. There are several policies that can be configured which you don't know. So if you have to keep checking that if something is wrong there, maybe you take our layers of security and say, okay, we are not layer 3, don't make layer 5. So they begin to ask several questions. The thing that is good for us to have a single sign-on, like I don't expect for me to be typing every now and then. People keep using it, but no matter what happens, just like you said, they are getting smarter.
I understand there is two-factor authentication applied in some cases, but this I'm talking from experience actually. There is one platform I logged in using open authentication. What happened was they just emailed me that I have logged into this platform using my email address. Not that am I the one or I should provide to some or I should input some authentication or nothing. They just emailed me that this email address was used to sign into this account. That's it. So in that case, what should you do?
Just like I said again, if the system notices that, okay, it might not be you, or it could have been you by mistake, because people just say, can I use your laptop? Somebody just log in. You don't know that it's capturing your credentials and stuff like that. Other thing you should know is that even most of when you are using single sign-on, there's something called token. It has expiration date.
I understand what you say, but you know, all these platforms had their own level of security.
Yeah.
not all these platforms apply the same level of security. Some applied exact what you're saying, and some applied exact what I'm saying. So in case of my scenario, what should someone do?
Well,
I would say, I think what he's saying already, he's got an information that apparently he's been compromised. In that case, you now take actions. You are aware that the system has been compromised. So what do? You may even get another.
No, from what he just said now, he has been compromised. The first thing he might likely want to do is to change the password. But unfortunately, if he changed the password, he has authenticated on different devices, on different applications. That means that same password will be exposed on that same platform.
They will all log out. They will all log out one. They will all log out. It pushes. Yes, it pushes those out. But it may not be the single sign-on that had exposed you, right? You could also have, really, it is advisable that if we want to generate our passwords, we use formulas. There shouldn't be just passwords that you creating the passwords can even remember. Right? It's not about you remembering your password. It's about you remembering a formula that you used. Or I think not. It may not be nomenclature. We talk about maybe cryptography, all those shift type files and all of those kind of. You can use some sort of formulas or formulae to generate your password strings. Right? So once you are interacting with a particular environment, you will now know that, okay, with my formula, this is the kind of password I may have used for this particular place, right? There are various ways to do that. But also, the single sign-on may not have been what has exposed him. So now that he has known that he only has a password, and that's why we advise 2FA or MFA, he will now take action, increase the level or the layer of his security. It wouldn't be just logging in with a password anymore. Once he has that single sign-on, he clicks on it. It gives him an information that it gives him maybe like a token that he said. It generates maybe on his device, another device, just whichever way it's on. He can now give access or notifications.
We are moving from HPC to cybersecurity, but it's actually part of it.
Yeah, it seems like I've been misunderstood. Being compromised and preventing to be compromised are two different things. My scenario was I was not. You understand? I've not been. That was the scenario. But the question is how to prevent that from happening. Because there are some platforms that use two-factor authentication and other security prevention methods, and there are some that doesn't use that. So in some cases, for those that doesn't use that, how can someone prevent himself? Like, for instance, all these network devices have prevention inclusion system, right? To prevent something from happening. So how can that be applied to us now? How can you prevent that from happening? Not that when it happened. When it happened, actually, those people that hacked your account, they are not stupid. The first thing they do when they hack their account, they try to deny you access. So you being fast to change your password, I don't think it will have anything. So how can we prevent that from happening?
Cybersecurity will not take the. So let me just take one or two comments. Let me just take the last two comments. Yes, but I love the discussion actually. But at least we are gaining one or two things. So let me just allow to talk.
Okay, yeah. So I think this thing, to my level of understanding, when you're talking about the platform that has two-step verification and all, your two-step verification should happen on your Google account itself. So even when you use this account on any other platform, it's taking its origin from the Google account. will definitely send you something, no matter the platform you're logging in. But you have to implement that on the Google account itself, not on any other platform now. Because I think I've experienced that. Maybe not really. My devices, my 2 devices were stolen, and so I went to my Google setting. I discovered a lot of things there. There are so many things that we don't check. There are so many things that we are not aware of. A lot of things. It was asking me a question that, how often should we send information about this? So even if you try to anything that is not even harmful, Google will send you notification immediately. Are you the one trying to log in this? Put in this, they will send you special code. Like special code will be sent to my system and it will be sent to my phone at the same time.
Okay, the thing is that for email and all those things, there are different ways you can actually secure it. Like she was saying, there's a way they can make it so secure that immediately there's a change, they will tell you. And even when the change is there, they still need to verify that it is you. That means that even when you try to sign in, tell you fine, go and check your email. And then even aside from that, there's some companies that, like Binance, for example, one of my friends, she almost she forgot her details. So when she try to change a password from another device, Binance told her that it's not possible unless you use the device that has been signed in before. That means that there is a way that you can also log into a particular device. That means that if it is not from this device, it will not accept it. You understand? So you can also put a kind of barrier that, aside from the email, you can also specialize on the fine. If it's not from this device or this particular location, it's not going to access it. You understand? So there are plenty protocols in place. Apart from 12A, you can also use location log. You can use even a device like this. But some one that you can do on your Gmail that even when you are offline, they will send you a code, a special code. So sometimes it doesn't have to be online at all. Like there are just different ways to do it. It doesn't have to be one side, but you need to understand how these things work. Because then it is the level of security that you set on the thing that will tell you, fine, this is what you can do. But if you don't understand some of those things, it won't work that way.
Okay, thank you. Okay. Oh, yeah.
Good one. I think so that because we have, I'm really impressed that this is becoming very interactive. That is the whole intention. So I think maybe we should just go back to the class so that we can also finish this class. We have another facilitator that is waiting. But you can continue this discussion after this session anyway, please. Feel free to do that. Because the reason why we came together is for us to have interaction, very quality interaction for that matter. So that is just what I'm going to say there. And the idea of, I know why cybersecurity is becoming a critical issue. We are going digital in all areas of our lives now. But with all the comments we are getting, I don't know why everyone is mentioning biometrics, which may take care of what you are talking about. What you know, what you have, and who you have. From what you said exactly. So I think let's come back to class now. Thank you very much.
Okay. I'm sorry. I thought my session is 2 hours.
Just 1 hour.
Oh, can you imagine? Okay. Let me just round up. Let me just rush over the remaining thing. I'm so sorry. Cyber security has taken the whole. So please. But it's interesting actually. So requirement for building an HPC. You know, if you want to build your HPC, like I said, for different application, for different approach, like a bioinformatician, there is something they are looking for. A geophysics, there is something they are looking for. Airspace, I mean, what do you call what do you call them? Aerospace, I mean. Yeah, that's what they are looking for. So these are things that will determine what are the kind of infrastructure, what are the kind of application that you are going to use to build your infrastructure. But we know that there are some basic things that made up high performance computing in terms of the hardware. Like I've said before, your storage, your compute cluster, and then some other few things. This is just like a cluster now. You have your switch, you have your compute node, different compute node bring like this now. We just form a cluster of compute node. Then this is your storage that will be attached. All these things will be connected via the network. Whatever you are doing, you connect everything via the network. Then you have different type of storage solution to achieve your, like I talk about storage here. This is storage, and in this workshop, we are going to be doing storage, as in building your own storage from scratch. We are going to also be doing that in this workshop. So you have different technology you can use in building your storage. You have ZFS, NFS, Ceph, and Lustre. Then you also have the network requirement. So, like I said, it depends on the kind of computational traffic that you want to be transferring between your node. That will determine, okay, is 1 gigabit per second be enough? Is it big data I want to use, or I want to transfer? You have different kind of thing you put into consideration, and then you have different technology. And then when you are building your network infrastructure too, you have to do some other kind of services, like your domain name service, the DHCP. Do you want those other devices or VM to be getting their IP via DHCP, and then the kind of file system you have to use? Sorry, I'm rushing this, but I just have to mention them. Then characteristics of high-speed HPC network. So there are things that you have to put into consideration, that when you are transferring your file, you know, there are times we talk about what we call edge computing, bringing your data close to your computing device for processing. So in such a case, the low latency has to be taken care of. You use a network that doesn't have latency, that the latency is also very low, that also have a very good high bandwidth between the node, because you want to be moving data between your nodes. So you have to use a technology that will make your data to be very, very fast in terms of transferring data. So we can talk about, these are the different kind of technologies that you can use. You can use a 10 gig, you can use 20 gig of, and then you have 1 gig. You can't be doing big data and be using 100 Mbps. Even 1 gigabit per second these days, that will not work well for you. So maybe you are just doing a kind of small kind of research within your own small cluster. Then you have fiber channel, you have Ethernet, then you have InfiniBand. InfiniBand is one of the technology that is being used today, but it has its own disadvantage too. But when it comes to big data, InfiniBand is one of the technology that we use currently. But you can read more of this thing. I will share this slide. Then, like I said, you have software component. I was saying it the other time. You have the kind of operating system you have to use. You have Red Hat, Linux, CentOS, all these. Okay, when you talk about Ubuntu now, I think it's a Debian distribution. Then the Red Hat, CentOS and Red Hat, they are more or less like the same. Then you have different kind of application library, the different type of tools you can use. You just, I will share this so that, because the next class is also very important. Then the job scheduler, there are different type of job scheduler, like I was saying, the traffic control. So these are different things you can use to do your job scheduling. Then these are just use cases: artificial intelligence and machine learning, medicine, financial services, and things like that. Then there are challenges in building your HPC. We can read on all this. Thank you very much.
Yes, we've taken the questions with your session already. Thank you very much, Engineer Bola. Let's put our hands together for him once again. Okay, maybe we'll probably have more time to interact with him, you know, as we go on.